Hello everyone, today we are going to move into section 11.3, which is talking about independent and dependent events. Before I get too far into our notes here, what we're really going to be talking about now is when we have multiple events happening. This is what we refer to as compound events, when we have one thing and then another thing happening directly afterwards, and trying to find out the probability that both those things occur. So let's go ahead and jump in. The first type we're going to talk about is independent events. Independent events are going to be some sort of events, so multiple, could be two, could be more, in which one event does not impact the probability of any other event. Okay, so this is probably our most straightforward type we're going to talk about today, where one probability happening or one thing happening does not change anything else. Some examples of these are things like flipping coins multiple times. The first coin does not impact the second coin, or if you use the same coin twice, that doesn't change the probability of the second flip at all. Things like rolling two dice. Okay, in general, those are independent, but depending on how we start to combine them, they may become dependent, and we'll talk about where that happens. The other one that's going to be important too is drawing cards, so like playing cards. But with this, we have to be very clear that we do it with replacement, meaning that we put the cards back. If we don't put the cards back, then we're going to have issues of finding the correct probabilities. Okay? So as far as finding the probability of two independent events, so knowing if A and B are independent, then the probability of A and B is the probability of A times the probability of B. Okay? Because these events are independent, they do not impact each other, we can simply multiply the probability of each event happening, and that gives us our total. Okay, what we really want you to think of here is that word and means multiply. So when you say the word and, we're talking about multiplication. Okay, moving into example 1 here. So we have a six-sided cube similar to our normal plane, or our normal die, or dice, but this one's labeled a little bit different. So it's 1, 2, 2, 3, 3, and 3. Four sides are colored red, one side is white, one side is white and one side is yellow. We want to find the probabilities first of rolling a 2 and then a 2. Well, if I look here, I have 2 of my 6 sides are 2s. So my probability of rolling a 2 in the first one is going to be 2 out of 6. Well, then the probability of rolling the second one is also going to be 2 out of 6 because the dice isn't going to change after the first one. I don't take that side off or anything like that. So now I have to combine these probabilities, and we have that word and in there, and so we multiply. Okay, now when we multiply fractions, hopefully you remember this, we go straight across. So 2 times 2 is 4, 6 times 6 is 36, and that technically is my answer. Okay, you could just leave it like that, or you can go to the decimal, which is 0.111, or 11.011%. Okay, so again, you can go either with the fraction, the decimal, or the percent. You could also reduce these. I'm not going to require you to do that. The 36 doesn't mean quite as much anymore as when we were doing our initial probability, so you could reduce, but I'm not going to force you to do that either. Part B. We're rolling now for the colors, so we want to roll a red, then a white, then a yellow. Well, red has 4 sides, so that's going to be 4 out of 6. White had 1 side, so we're going to do 1 out of 6, and yellow was 1 out of 6. And you can see I'm already putting the multiplication in there because I'm combining these events together. So you can go ahead and multiply 4 times 1 times 1 is going to be 4. 6 times 6 times 6 is 216. So this is 4 out of 216, which reduces here if you want it to 0.0185 or 1.85%. Okay, so that's independent. Those ones are going to be pretty straightforward. The biggest thing you have to decide there is making sure that they truly are independent. That rolling one doesn't change the probability of the other, which in this case should be pretty clear that the dice isn't changing in between those events. Okay, so let's talk about the other one because it's a little bit more difficult. Let's talk about dependent events. Dependent and independent are definitely opposites of each other. So if you think about this definition, you can probably pick out what a dependent event is going to be. It's simply going to be an event where one event happening impacts the probability of another event. Okay, so we're going to say these are events in which one event occurring, we'll say impacts. Impacts the probability of the other event. Okay, event, or it could be more than one event if we have multiple events happening. Okay, so basically the probabilities are going to change based on the first thing happening. So let me give you a pretty clear example of this. Okay, so we're going to be talking about there's 2 lemons in an orange in a bag. If you pull out 2 pieces of fruit, the probabilities actually change based on the outcome of the first. So to give you an example of this, I actually printed out some lemons and oranges here. We'll go side by side here. So I have 2 lemons, 1 orange. Okay, we're going to pretend these are all in one bag. So I basically have 2 things that can happen from the start. I can pull out a lemon, okay, which leaves me with 1 lemon and 1 orange left in the bag. And then the second draw is going to be 50-50 because I could pull the lemon or I could pull the orange. To make this really clear, though, let's look at what happens if I pull the orange first. So by chance, if I pull the orange first, now I'm left with 2 lemons. So I'm guaranteed to get 11 on the second chance. So right there, I can see that that second probability is either going to be 50-50 or it's going to be 100% for the lemon. And that difference is our dependent probability or dependent event kind of showing up there. Okay, we can also show that in what we call a tree diagram. That's what we have right here. Okay, I can see that from the start I have 2/3 going towards the lemon because 2 of the 3 are lemons and 1/3 going to the orange. So if I pick a lemon first, then it goes to 50-50, 1/2 each because I have 1 lemon of the 2 left and 1 of the oranges left. Okay, if I pick the orange first, though, that means that all I have left are the lemons, so I'm guaranteed to pick a lemon, and it's impossible for me to get a second orange. Okay, that change in probability that happens from this first split to the second split is what's happening in our dependent events. Okay, now when that happens, we get this thing called a conditional probability. Okay, so the conditional probability is written this way: P of B with a line A. Okay, that line in the middle, okay, which you can actually see here if you want to see what it looks like typed out. Okay, that means that this is the probability of event B given that event A has already occurred. Okay, so the way I want you to think of this, so this is our symbols, this is what it's actually telling us, but what I want you to think of is this is an adjusted probability. Okay, it's the adjusted probability for that second event after the first one has already happened. Probability, if I can spell it here. Okay, so it's our adjusted probability for the second event saying that the first one has already happened. Okay, now that ends up showing up here in our dependent events and how we calculate it. So we are going to still multiply because we're still using that word and, but if these are dependent, then I have this conditional probability here, which is my adjustment. Okay, so this is the conditional or adjusted probability. Okay, and that's really the way we're going to think of these as we go. Okay, so we're going to move into another example here where we have to decide if things are independent or dependent and how that actually changes our math as we go through these. Okay, so let's go to the back here. Number 2. Okay, number 2, we have 2 cards are drawn from a standard deck of 52 cards. Determine and explain if each event is independent. Okay, now before we get too far into this, I want to show you this paper here, and you'll have access to this as well. This is what we refer to as our sample space sheet. Okay, so if you want to write that on here, this is what we refer to as our sample space. Space, if I can spell today. Okay, and this basically gives you 2 things. It gives you a chart here of when we're rolling 2 dice. We'll use that in a little bit, but I want to focus on the cards here. Okay, for the cards, we have 4 suits. We have hearts, diamonds, clubs, and spades, and you can see the symbols that go with them. Hearts and diamonds are both red. Clubs and spades are both black. Okay, and so I gave you all of that information because a lot of times they ask you questions about playing cards and not everyone's familiar with it. So if you need to look at this diagram, we will consider aces down here, the A's, to be high cards. Sometimes you consider them to be lows and ones, but we're going to consider them to be the highest. Okay, and then we have kings, queens, jacks, then 10s, 9s, 8s, all the way down to 2s. Okay, so our first question that we have here for example 2 says explain, selecting 2 hearts when the first card is replaced. Well, if I look at my hearts here, okay, I can count them. There are 13 of each suit, okay, which might be something you want here. Is 13 each suit. Okay, there are 52 cards total, which is also a good number to know because we're going to use it quite often. And so what's going to happen here is if I use all of my hearts, well, I could pick any of the 13 hearts to start out of my total of 52 cards. And now that's my first event. My second event is pulling another heart. But what's important is what's happened after the first one. Because after the first one, if I pulled out, say, a jack of hearts, I'm then going to put that jack back in, and now I still have a total of 52 cards, and I still have 13 hearts to choose from. So then we can go ahead and multiply those. Going across the top, 13 times 13 is 169. 52 times 52 is 2704. You can do those on your calculator. Eventually you'll get used to those numbers because we use them quite frequently. Okay, so this is my probability. You can divide that out. You could reduce it if you want. It's technically 1 over 16. Okay, but you can go to the decimal, which is 0.0625, or the percent, which is 6.25%. Okay, so just like before, fraction, decimal, percent, anything is good with me. Okay, let's go to part B though. Selecting 2 hearts when the first card is not replaced. So the big difference here is now I'm talking about not. Okay, and I actually skipped a part here in part A, and we'll come back to it here in just a second. The real difference is now that I don't replace that first card, my first event is still 13 out of 52 because I'm starting with a standard deck to begin with. But what happens if I don't put that first card back? Well, now I only have 51 cards total, and I only have 12 hearts because I pulled one of those hearts to begin with. And so now this probability has changed. Okay, that change probability means that this is now dependent. And the reason I know it's dependent is there is not replacement. So replacement is usually a giveaway as far as whether it's dependent or not. If it's not replacement, it's not independent, it's dependent. If there is replacement, then it's independent. So our first one here is independent. And we know that because there is replacement. Okay, so here we can go ahead and multiply again. 13 times 12 is 156. 52 times 51 is 2652. Okay, you can divide that out. This is 1 over 17. So you can see your probability goes down just a little bit there, which is now 0.0588 or 5.88%. So again, you can see your probability goes down just a little bit because you didn't put the first card back. So now you have a slightly lower chance on that second draw of getting a heart. Okay. Let's do one more with playing cards here. We have a queen is drawn and is not replaced, then a king is drawn. So a queen, if I go to my sheet here, there are 4 queens. Those are my cues here, 1 of each suit. So I would have 4 of those out of my total of 52 cards. Okay, but I'm not going to put the card back, which means there's now 51 cards. And then I need a king. Well, the king, there's still 4 of them because the first card I pulled out was a queen. So I still have 4 kings. So it's 4 and 4, which is going to give me 16. Over that same 2652. If you want to divide it out, it's 4 over 663, okay, or 0.0060, which is 0.6%. So pretty small there. Okay, and so doing things like this, you can actually figure out a lot of probabilities, specifically with things like poker, where there's very specific patterns to how things are run. You can figure out probabilities of different hands happening and stuff like that. Okay, so pretty useful thing here. Let's talk about rolling dice. And we have 2 dice that are rolled. I'm going to give them each a color. I'm going to call one white and one red. That's just so we can talk about the difference between the two. And we want to determine and explain if each one of these is independent or dependent, and then find those probabilities. So let's go ahead and look here. First of all, we need the white cube to show a 6, and the sum is greater than 9. Okay, well, if I pull out my sample space sheet here, we're going to look at this top diagram now. You can see that all of my dice are white, kind of in the same number going down my columns. The red go across the rows as far as the same number, and you get all your combinations here. If you count them 6 by 6, there's 36 total here for your dice. Okay, but I specifically want to think about just the white dice first. Well, the probability that the white dice shows a 6 is going to simply be 1 out of 6 because I have 6 options for that first dice. Okay, now the sum being greater than 9. This one's going to be a little bit trickier. I need to look, greater than 9 means 10, 11, or 12. Sum means I'm adding them together. So now I've already said that the 6 has happened. So I'm going to ignore the first 5 rows of my table. I'm looking at just this last column. And I can see that I have 10, 11, and 12, these last 3 places here. So of these 6 options, 3 of them work of the 6. So we can multiply that out, and I get 3 out of 36. Okay, you can divide that out. It's going to be 0.0833 or 8.33%. Okay, and that's for these 3 options here at the end. And you can actually see that it's these 3 out of my total of 36. Okay, so that 36 does have a little bit of meaning here. So then the question is, well, is this thing independent or dependent? Well, the fact that we narrowed it down to the 6 first means that this is going to be dependent because there's only 6 options here where my probabilities actually work. And so, or I get that sum greater than 9. And so by narrowing it down, if I would have said that it's a 1, that means I can't get a sum greater than 9. And so that first dice did actually change things here. So we're going to say this is dependent. And now we're going to say that a red cube is even, and the sum is 5. So red cube is even. Well, that's going to be 3 out of 6. Okay, and that the sum is 5. Well, sum is 5 is going to be 1, 2, 3, 4 here on this diagonal here. I have all sums of 5. I can have 4 and 1 or 2 and 3 in any combination there. So that's going to be 4 out of my total of 36 options there. Multiply that out is 12 over 216. It's the same thing as 0.0556 or 5.56%. Okay, now this one again is going to be dependent. Okay, because I can only pick the 2 where my reds are even. Okay, and that's changing what options I'm allowing out of everything. Essentially what I would say is that anytime you're combining both dice together, whether I say a sum or a difference or anything like that, now you're going to be dependent. If I said what's the probability of the white dice showing a 6 and the red dice showing a 5, those are completely independent. Okay, and so you got to be careful with those ones. But if as soon as you're combining things together in any way, it's going to be dependent. So my last one here is very similar to the first one, but I want to show you the slight difference of what's happening here. It says that the sum is greater than 9, given that the white dice shows a 6. So this is actually only a single event. So I can't really talk about independent or dependent for this one, because I'm giving you that the white dice has already happened. So what I'm asking is simply, when is the sum greater than 9, knowing that the white dice is already a 6. So again, I'm going to cover up the first part of my table here. I'm saying my white dice has to be a 6. How many of those 6 are greater than 9 when I add them together? Well, that's those last 3 again. So it's simply 3 out of 6, 0.5, 50%. Okay, and so this right here, this is our conditional probability, which is the same 3 out of 6 that you see right here. Okay, up top. Okay, so that's really that same probability. We didn't think of it that way, but that was that same piece. Okay, last one we want to talk about here is the table. This is another common type of question that you're going to see. You'll see it on your homework and on your practice and quiz as well. So we have this table. This one shows the number of teachers, coaches, and students at a select high school for each gender. Which of the probabilities, or finding the probabilities of the following. So we're going to start with that a coach is male. So we're starting with coaches, and we're saying that they're male. So my total is out of all the coaches, so I need to add those together. Well, 17 and 9, that gives me a total of 26. At the bottom here, I get 26. Okay, and my males, there's 17 of them. So my answer would be 17 over 26. And you can just leave it like that. You can go to the decimals if you want, but for the sake of time, I'm just going to move forward. Okay. Next, I have a person is a student given that they are female. So this given that they are female, this narrows down your total right away. So that means I'm ignoring all of my males here. My total is going to be all of my females added together, which I've already done the math for you. It's 486. So that is going to be my total, is 486. And my students that are female are 453. So 453 goes on the top. Again, that's your probability because I'm given that they are female. I have to narrow down before I go to figure out my other piece. Okay, that's different than just saying a person is a female student. Okay, I'm still talking about this 453. Those are my female students, but now I haven't narrowed it down to females to start. So now I'm out of everything. So I would add up all of my males here as well, which I lost that number. 12 plus 17 plus 429 gives me 458. 458. And if you add those two together, you get 944. So my total here is out of everyone, which is 944. Okay, so that slight change in the wording has a very big impact. So given narrows your total to whatever that group is. And then if there is no given, or I don't tell you that it's a specific thing to start, that's the difference. Okay, this first one here is actually conditional as well. I could say, what is a person is a male given that they're a coach. I'm starting by narrowing it to coaches. Let's go to D here. A person is a male given that they are a teacher. So now I'm narrowing to teachers. So I would add my teachers together here, which is 36. Okay, 12 of them are male. So we would have 12 out of 36, which is 1/3 or 33% if you want to go there. So that is how to work with a table. Okay, these are independent and dependent probabilities. Again, the big thing is we are multiplying all of our probabilities together when we need to, if we have those multiple events. And if you have any questions with this, feel free to reach out and we will get those taken care of for you.